today we're going to look at a complete example of another implementation of a quantum process. The idea is to exemplify the concepts of states and dynamics and trajectories on block spheres and measurement in another platform. We've already seen a Mark-Zehnder interferometer, quantum states coming in, there are certain optical elements that are transforming the states, and then you do final measurement at the end. And you were able to see interferometry as well. So let's look at another example. This example is meant to consolidate some of the ideas that you've already seen. So it's like an example quantum process. Cast in a physically manifest setting. So let me explain what this means. So we're going to look at an example in a spin half particle. The nuclei, subatomic particles, electrons, protons, even photons, they have a property called spin. Right? And I talked about spin in the first class. The spin makes, say, an electron act like a tiny magnet, a dipole. So if I were to just in caricature form draw this electron like a magnet, which is represented by an arrow and is quantified by this symbol called the magnetic dipole moment, then see how this thing behaves inside a magnetic field. Now, in order to motivate why is this a magnetic moment and what are the units of this physical quantity, I would like to give the example of a charge Q that is moving in a circle of radius r. Alright, so now is this charge which is moving with a certain speed v in an orbit of radius r, can we say that this is a current? It is. So this charge moving in a circle is like a current, I. Now, one question I would like to ask is, will this current loop act like a magnet? Yes, it's going to act like a magnet. So if this is a positive charge and I curl my fingers in the direction of motion, then this finger is going to point, the thumb is going to point in the direction of the magnetic field. So there will be a magnetic field coming out. So if I were to draw this in perspective, if this were my charge and the arrow shows the direction of motion, then a field is going to be developed which will look something like this. It's going to loop back onto itself, no doubt about that. That's a property of magnetic fields. So this current carrying loop is like a tiny magnetic moment, like a magnet. And if I were to define a magnetic dipole moment, mu, for this tiny dipole moment, and I'm just looking at the scalar here, not the vector, then I would know that this magnetic moment is going to be the current multiplied by the area of the circle, which is pi r squared. So it's current multiplied by the area. The loop is on the outer periphery of that area. That's the definition of a magnetic dipole moment. So what are the units of the dipole moment? Ampere meter square. Alright, and we can also correlate the current I with the charge and the speed. So what is current? Current is a charge that passes through a certain point per unit time. Now how long does it take for the object to go around? So if 2 pi r is the length of this loop, then the time it takes will be 2 pi r over the linear speed. Correct? So hence, the magnetic dipole moment for this current carrying loop could be written as QV 2 pi r square, the pi's go away, one of the r vanishes, and I'm left with QVR 1/2. And if I do something else, I make this Q over 2, put an MVR and put an M here as well. It's not going to make any difference. So this product of mass, velocity and radius has a special name. What is that? It's called the angular momentum. Right? So mass into velocity is the momentum. You multiply it with the moment arm, you get an angular momentum. So this is really Q over 2m and the orbital angular momentum. So the magnetic moment is proportional to the orbital angular momentum. And if I would like to put a vector sign on this, this is what the magnetic moment really is. So any object which is charged and has an orbital angular momentum will also act like a magnet. And this is the relationship where Q over 2m is a constant of proportionality. Alright? Now if you look at an electron, so by the way, if this electron is inside an atom in a particular orbit, its angular momentum has to be quantized. And you know this from basic chemistry that if you just look at the electron inside an atom, its angular momentum L is quantized in units of ml h bar. The h bar is the reduced Planck constant, and ml is just some quantum number, probably an integer. So this mu is equal to Q over 2m ml h bar, or QH bar to the mass of the particle ml. So if ml is quantized, ml takes up certain integer values, 0, 1, 2, -1, -2, then this object is also quantized. The magnetic moment is also quantized. Now the electron or the proton also has angular momentum in addition to orbital angular momentum. And that angular momentum is its intrinsic angular momentum, which is called the spin. Right? So you just have an electron that is isolated, not inside an atom, standing there on a quantum dot, and it's blocked there, it's just sitting there. It will still have an angular momentum, which is called the spin. So if the orbital angular momentum, by the way, can be 0, you know that very well, because in the lower shell, the shell that is closest to the nucleus in an atom, the big L is 0, so ml is 0. So orbital angular momentum can be 0, but still there is some magnetism associated with the electron, even if its orbital angular momentum is 0. So that magnetism comes from the spin. So this is the magnetic moment associated with the orbital motion. But there is a magnetic moment associated with spin as well. So spin as a quantum operator as well. So just like orbital angular momentum, the spin angular momentum. For short, it's just called spin. But now we're talking about spin. We would like to put in another constant here, because the proportionality does not hold. You have to multiply this with another constant that comes from atomic physics, which is called the Lambda G factor. But that's more atomic physics, so I'm not going to go into the details. But whenever you have spin, you're going to have magnetism. So a magnetic dipole moment always comes with the spin. So for an electron, by the way, so let's focus, say, on a proton. For a proton, Q is plus E, where E is the charge on the proton, and M would become the mass of the proton, and G is, it comes out from spectroscopy experiments to be almost equal to 5. And so if this means that mu equals G E 2 over the mass of a proton S of a proton. Now, how do you know that this magnetic moment exists? You can do an experiment. So when you have a proton or an electron and you pass it through an inhomogeneous magnetic field, then this beam of protons is going to split. This is called the Stern-Gerlach experiment, done in 1932. You might have studied this in your modern physics class. Anyway, so you can do an experiment to tell that your particle has a spin and therefore a magnetic moment. Now, what does this have to do with quantum computing? So that's what I'm getting at. Suppose we focus our attention on a proton only. Now, for all practical purposes, this proton has a magnetic moment mu, and we've done a slight digression in order to understand where is this magnetic moment coming from. That's from atomic physics. But now we enter the quantum information world, so we know that this proton acts like a tiny magnet. Okay, so all of this is background. Now, what happens if you put a magnet inside a magnetic field? Okay, ideas. In a homogeneous magnetic field, the field lines pointing in the same direction, same field density everywhere. The field is B. What's going to happen to this magnetic moment? Will it respond to this magnetic field?
It tries to align with this.
Right, it tries to align with the magnetic field. So it would like to have its magnetic moment parallel to the field. But there's also another configuration that's possible, which is anti-alignment. So this is alignment and this is anti-alignment. But the preference is to align with the magnetic field. Now, why is that the preference? Because that lowers the energy of the system. So a magnetic moment would like to, a compass needle at any point in space would like to align in the direction of north sub. So here is north. So if you like to point in this direction. Okay, in fact it will slightly tilt because the magnetic field is not really horizontal in Lahore. It's going to be horizontal on the equator, it's going to be vertical on the poles, but it's slightly at some angle, 30-40 degrees. So it's going to align itself with the magnetic field, the local magnetic field. So exactly this proton spin, since it's a magnet, it wants to align with the field because that's the lowest energy configuration. In fact, physicists are clever. They like to quantify everything. So physicists tell us that the energy of a dipole inside a magnetic field is given by some relationship between mu and B. What could that relationship look like? Mu dot B, okay. So mu is a vector, B is a vector. Is this the correct relationship? With the minus sign, because you want alignment and that alignment makes the energy go down, negative. And when they are parallel, this energy is maximum. So what you could do is, you could say that the energy of the proton spin inside a magnetic field will be represented by two levels. One level is when the spin is aligned with the field, and the other is when the spin is anti-aligned with the field. And there is a gap in energy between these levels. And that gap is delta E, let's call it delta E. G. Yeah, sorry. So this is anti-parallel and this is parallel. Okay? For electron it will be the opposite, but we're talking about a proton here. So there's an energy gap between these levels. And that energy gap is going to be 2 times mu b. But now I've removed the dot product and the energy is a scalar. So this is an energy gap. Got it? So this energy is plus mu b, the angle is 0 degrees. The angle is 180 degrees. Cosine of 180 degrees is -1, so this becomes plus mu b. This energy becomes minus mu b. So the separation is 2 mu b. And any energy can be written as h bar omega or hf. So associated with energy there is a frequency. So now what we have is we're looking at a single proton placed inside a magnetic field, and we've come up with the idea that its energy is quantized. The energy can take up 2 values. And we can also assign a quantum state with each configuration. One of these states, let's call this state ket 0 and let's call this state ket 1. So ket 0 really corresponds to parallel alignment of the proton spin with the field, and ket 1 corresponds to the opposite configuration. In space it's anti-parallel, it's anti-aligned, but in the Hilbert space or on the Bloch sphere, these states are orthogonal. Orthogonality in the Hilbert space does not really mean being 90 degrees apart. So orthogonality, as you know, has a special meaning. आपको थोड़ी परेशानी लग रही है, समझ नहीं आ रही? हाँ, आ रही है, ठीक है? So now what we've done is we've looked at another physical example of a proton spin inside a magnetic field, and we've seen that this also has 2 quantum states, and they are given certain labels, ket 0 and ket 1, and these quantum states can live on the Bloch sphere. So now this is an abstract mathematical concept which allows us to pinpoint the quantum state on a Hilbert space or on a Bloch sphere. So we could also have arbitrary states. We could have this state, psi equals anything, C naught ket 0 plus C naught ket 1, and so on. So now we have another physical example of a quantum state. Our relevant degree of freedom that we're talking about here is the spin of a proton. Now when we have this form of energy, right, or you can also write this as minus h bar omega over 2. Or if omega is positive, we can so this becomes plus minus h bar omega over 2, right? The 2 energy levels. One is the higher is h bar omega over 2. This is minus h bar omega. That's how we define this frequency omega. So any energy gap can be written as h bar omega, hf. It's dimensionally correct. Alright. Now what we would like to do is come up with this idea of quantum dynamics. We've seen that quantum states exist for this system, and they can be anywhere on the Bloch sphere. This could be your general state. Your C0 and C1 are probability amplitude and all the normalization constraints are followed. Alternatively, if you're fond of talking about geometrical angles on the block sphere, you can write this as cosine theta over 2 ket 0 plus sine theta over 2 e raised per I phi ket 1. And physically this would mean that the spin is in a superposition. And ket 0, this axis, the ket 0, ket 1 axis is really, these states are defined by the orientation of the magnetic field. So now we are connecting a generic mathematical scenario with a physical reality, which means that we have come up with this idea of kets and bras and block spheres. This is something generic, right? It's mathematical and it can take up different forms. ठीक है, ये हमने पहले बात की तस्वुर की, अब हम बात करें तस्वीर की, समझ गए? So we have a generic situation, we described a generic situation, now we're looking at one particular physical technological platform. Another could be the spin of an electron, or the path of a photon, or the direction of current in a Josephson circuit, or anything else. Okay? So now we're looking at the spin of a proton. Now, this is called a spin half particle. A proton is a spin half particle. That's why we have this 1 over 2 here. Spin half particle means when you put it inside a magnetic field, you get two possible configurations, two levels. Okay? So if you have a spin S particle, you will get two S plus 1 levels when placed inside a magnetic field. And you might remember this kind of expressions, they appear in when you study the hydrogen atom and so on. Spin half particle will have two S plus 1 configurations. Spin 1 half, this becomes 1 plus 1, 2 configurations. And that's what really is a qubit is. It's a two-level quantum system. So now we have a physical picture, we have an energy level diagram, we have an energy expression, and we have quantum states that live on the block sphere. G. So if you have a spin S, how many possible values of ms exist? 2s plus 1. If you have spin half, there are two possible values of ms. If you have orbital angular momentum L, you have 2L plus 1 possible values of ml. So the 2s plus 1 possibilities are generally represented by ms plus 1 and ms minus 1. So these are spin quantum numbers. Got it? So by the way, this is really nice here. So you ask this question. If I look at this expression, so if you have a proton and it's not inside a magnetic field, you don't know which direction the angular momentum is pointing in. In order to know the direction, you need to have a direction. But if you have no field, you have no preferential direction. Because space is isotropic. It's the same everywhere. So in order to define a direction, you need to apply a magnetic field. Because the magnetic field is an axial vector points in a certain direction. So when it points in a certain direction, you can find out the component of S on that direction. That's called, let's say that direction is called the Z direction. So then what you would have is inside a magnetic field, say pointing along the Z direction, this S, we're just talking about the Z component of S, this becomes GE over 2m, the mass of the proton, and this now becomes the Z component of the magnetic moment. Okay? And we know from basic quantum mechanics that this has to be quantized. This thing has to be quantized. So GE, this is quantized according to ms. h bar 2 mp. Alright, so this is really what the magnetic moment looks like. So I can put this as gh bar EMS over 2 times the mass of a proton. Okay? This is what the z component of the magnetic moment looks like, and actually you can put in values. So ms could be plus half, minus half, mp, you can put in the mass of a proton, and you know what the value of h bar is, you can put in the value of g for a proton, which is about 5. You can actually find out what mu is in ampere meter square. It's a small number, very small number. And if you were to do this for an electron, so this is some atomic physics just for the curious minded, because I'm also an experimentalist. I like to connect all of this with what's happening in the lab. So if you want to do this for an electron, you will have to use a minus sign. The G for an electron is 2, the value is 2, h bar, E, ms is again plus minus half, because electron is also spin half particle. Another 2 m electron. Now we have m electron, the mass of electron. This 2 cancels out. Since ms could be plus minus half, I just put a plus minus here, and this turns out to be plus minus h bar, the charge of electron, divided by 2 divided by the mass of electron. This is the smallest unit of magnetism. Alright? So this is called the Bohr magneton. It has certain value. 9.27 in 10 to the minus 24 ampere meter square. Yes. Because G is equal to 2 for an electron, roughly. In fact, this is one of the best known constants in all of physics, G. There's some fine corrections to this because of relativistic electrodynamics. Anyway, so now what we know is that the magnetic moment can take up 2 values for an electron or a proton. And how can you tell? If you have protons coming into a magnetic field, since there are 2 possibilities, the beam is going to split in 2. Because the energies are different. When the energies are different, forces are also different. One is a positive force, the other is a negative force. Because the force is related to the energy. And then the 2 beams split out, and you get 2 spots if you were to detect those 2 beams by some measure. That was a Stern-Galag experiment. In fact, that was how spin was discovered. Yes.
Sir, the proton would want to achieve a state of minimal energy in a magnetic field. Why would it exist in that Cat 1 state in the first place? Wouldn't it operate in that series?
Right. Okay, very good question. Really very good question. So this brings in some statistical mechanics. What major are you? Physics. So this brings in some statistical mechanics. You have 2 energy levels. Right. So this energy is say E1. This is a high energy E2. And this system is at some temperature. So it's not that at 0 kelvins, of course, only this energy level is going to be populated. The possibility of this state being populated is 0%. But there is a distribution. So the fraction of electrons or particles in the lower energy is going to be given by exponent minus this energy E1 divided by Boltzmann constant over T, and you normalize. So you normalize by adding both of these things. So you normalize in this fashion. So if you would like to make a plot of this temperature, the fractional population in this lower state F1 at 0 Kelvin, it's going to be 100% or 1, and then it's going to drop off exponentially. This is called the Maxwell-Boltzmann distribution. So that's why there is still some finite probability that this state is occupied. So that's because of temperature, but it's also possible that you give it a nudge yourself. So you can stimulate with external radiation so that the spin flips. That's what you do in a magnetic resonance experiment. Okay? Alright, so now armed with this description of states, any questions about the state picture? You've connected it somehow with quantum information, with quantum states, labeled these states, and we know that superpositions can exist. Any further questions about the states before we move on to the dynamics? Alright. Now, in order to look at the dynamics or logic gates, which are unitary transforms, so let's now focus our attention a little bit on the dynamics. In order to look at the dynamics, we generally have an equation of motion. We know that we're going to get a rotation operator on the Bloch sphere, which will describe how this state is going to transform. But let's see where is the dynamics coming from in this physical system. So what is the meaning of dynamics? क्या मतलब dynamics का? Change in time. So when something changes in time, there's generally an equation that is called the equation of motion. So one equation of motion, examples of equations of motion. Newton's second law is an equation of motion that tells us how the position changes with time. Another equation. So what is the analogous equation of motion in simple non-relativistic quantum mechanics? The Schrodinger equation. So the Schrodinger equation has to describe the quantum dynamics and see whether it gives the same unitary rotation operators as we learned about in the previous classes. So what is the time-dependent Schrodinger equation? Anyone? So give me something simpler. I mean, is this alright? Right? So this is the time-dependent Schrodinger equation. So anyone who hasn't seen this equation before, don't be shy, I can give you some reading material about it. Alright, Abdullah, in any case, we need to give them some reading material from modern physics, basic first year book. Okay? So this is the time-dependent Schrodinger equation. It is the equation of motion for a quantum state that is changing with time. And we want to solve this equation. So this object here is called the Hamiltonian. And the Hamiltonian is an energy operator. And we already know what the energy is, minus mu dot B. So the energy is going to be an eigenvalue of this Hamiltonian operator. Right? So the energy, so if you find the eigenvalues of this Hamiltonian operator, it's going to be the energies. Alright? And the Hamiltonian, so we need to find out what the Hamiltonian is, okay? We need to find an expression for the Hamiltonian. So the first thing is, let's find out the solution of this equation. So forget about everything else. Suppose I have some constant a and I put d y over dt equals b y. So this is a differential equation. A and b are constants and y is a function of time perhaps. So these equations look similar, correct? So what's the solution of this equation? So what do you mean by finding the solution of this equation? So you solve it, so when you solve it, what will you get? You will not get an equation, you get an expression for y as a function of time, and that function is going to tell you how does y look in time. So what's the solution here? Exponent. Can you guess what the solution is going to be? B. The minus sign, because if you take this to the other side, and where is the variable? What's the variable here? See, where does that come? In the exponent, right? With some constant y naught, say, which is the value of the function at time t equals 0. So that's what the solution to this differential equation is. Got it? Likewise, the solution to this time-dependent Schrodinger equation can be written down just by inspection, just by looking at this solution. So can you please write down the solution by looking at this? What should I write over here? Yeah. नहीं देखें इसको यूं मान देगा ना. So there's a minus sign, right? कोई बात नहीं, we already know how to exponentiate matrices. Why not? So why can't we exponentiate a Hamiltonian? We can. So just by inspection, by pure analogy, write down the solution for the time-dependent Schrodinger equation. You don't have to be fearful about putting a matrix or a Hamiltonian or an operator in the exponent. We've already seen that in the previous lecture. You put poly operators in the exponent, didn't we? Alright, so the solution would be the quantum state as a function of time will be equal to exponent minus iota minus iota Hamiltonian t over h bar. So this iota was really with a positive sign in the denominator. I moved it up, got a negative sign. This operator acting on the quantum state at time t equals 0. So if you're not comfortable with this, what you could do is you could take this as a trial solution, find the derivative of this. Right? This would be constant for the purposes of derivative. and see if we recover this equation. So imagine this was a trial solution. Take the derivative of both sides and figure out whether this is indeed a solution to this equation. Yes. This one? So if I differentiate this, so let's do that. dy over dt is y naught is just e minus bt over a. It's minus b over a. So this is a dy over dt, a dy over dt equals minus y naught b e minus bt over a, but y naught, so this is minus b by, alright, so this should be plus. But that's correct. Okay? Please excuse me for these algebraic typos. So this is the Schrodinger equation's solution. What does it mean? It means you have a quantum state psi. You start off at time t equals 0 with this state. And with time, it evolves. The state evolves into a new state. On the block sphere, you start off at time t equals 0 with some state psi 0 and you switch on a Hamiltonian. Now this Hamiltonian is now coming because of the magnetic field. So we have to understand that, and we'll make that connection clear in a minute. So you switch on the Hamiltonian, and under the influence of that Hamiltonian, time starts ticking and the state starts to evolve with time. And when it evolves with time, it takes some trajectory. You don't know what the trajectory is, it depends on the Hamiltonian. It takes some trajectory and ends up somewhere else, possibly on the block sphere. And whenever you start your clock, it's at time 0. When you stop, it's some time t has elapsed, and you will find out that your quantum state has evolved to a new position on the block sphere. And what is driving this evolution? It's the Hamiltonian. So the Hamiltonian drives the evolution. It generates time evolution. So Hamiltonian is an operator that generates time evolution. H generates time evolution. Now the energy of a particle inside a magnetic field is given by this, h bar omega over 2. But now the magnetic field can point in different directions, and the Hamiltonian needs to be an operator as well. So in quantum mechanics, if you had a magnetic field pointing in the z direction, right? So that's our first assumption. The field is pointing in the z direction. P. Then the Hamiltonian will be given by a matrix with an operator that is h bar omega over 2 sigma z. Sigma z is the poly operator, poly z operator. Alright. the field is pointing in the x direction, it's going to be equal to h bar omega 2 sigma x. Where this omega, this thing omega, depends upon the magnetic field B, right? So you can find out the relationship between omega is 2 times mu h bar 2 mu B. So it's proportional to the magnetic field. Stronger the magnetic field, higher will this frequency be. So what we have now is we are able to find out what the Hamiltonian of the system is depending upon the direction of the magnetic field. So the Hamiltonians, the direction of the magnetic field is incorporated within this matrix here. And the strength of the magnetic field is incorporated within the value of omega. And omega is proportional to the strength of the magnetic field. That's called the Zeeman effect, by the way. So if, coming back to this example here, two energy levels, if the magnetic field is higher, this gap is going to get higher. Higher and higher as the magnetic field goes up. Okay? So the gap is proportional to the magnetic field. That's called the Zeeman effect. If there is no magnetic field, then these two levels are going to be degenerate. Right? You will not see any of this quantum computing stuff. So now we have decided what the Hamiltonian is. The Hamiltonian depends upon the direction of the magnetic field, because that determines what matrix the Hamiltonian takes. And the strength is determined by omega. So now if we put this in here, we assume for a minute that the field B is parallel to the z direction. You start off with a state psi 0. After some time t has elapsed, a new state is achieved, and that state will be given by exponent minus iota. Let me do this properly. H, so this is my Hamiltonian here because the field is in the z direction. H bar omega over 2 sigma z, which is a matrix. I want to put time here as well. Put an H bar here. So now I have a matrix operator acting on a quantum state. And if I were to do some nice cancellation, this H bar just goes away, just withers away. This omega, by the way, is minus gamma b, where gamma is called the gyromagnetic ratio, and it depends upon the Bohr magnetons, but this is coming from geometric physics. You can actually put this as a homework problem. What is the value of this omega? I'll put this as a homework problem. Anyway, so I will get e raised to power minus I omega t over 2 sigma z acting on ket at time t equals 0. This is my state evolution under the action of a magnetic field. Is this a unitary operator? First question, is this a unitary operator? Yes. Is this a rotation operator? Why is this a unitary operator? Because if I were to take the inverse of this, so first question, is this unitary? If I were to take the inverse of this, sigma z, the inverse of this is E plus I omega t over 2 sigma z dagger, right? The dagger of sigma z. So what I've done, when you take the dagger of something, so I want to find out whether the dagger is equal to the inverse. So when I take the dagger here, it's going to change this minus iota to plus iota. Sigma z dagger, but sigma z is Hermitian, which means you take the complex conjugate and transpose, it's going to give you the same state. So it's Hermitian. So this gives me E plus I omega t over 2 sigma z. Now is this the inverse of this? Is this operator the inverse of this thing?
Yes.
It is. Because if I put both of them together, one after the other, I will get identity. So this is indeed the inverse of this. E minus I omega t over 2 sigma z inverse. So the dagger of an operator, if the adjoint of an operator is equal to its inverse, then the operator is unitary. And that is because this sigma z is Hermitian, its dagger is the same as it. It doesn't change. So this is a unitary operator. So is it a unitary operator? Yes. Is the evolution unitary? Yes. How do I reverse this operation? I just let time run backwards. I have to change this minus sign to a positive sign, which means I have to change time so that it runs backwards, or change the sign of the frequency. Anyway, so this is a unitary operation, but is it also a rotation operation on the block sphere?
Yes.
Why? It is a rotation operation because what you observe is you have an axis of rotation. What's the axis of rotation? The z-axis. And what's the amount of rotation? It's omega t. Our definition for a rotation operator is exponent minus I beta amount of rotation with some polyoperator divided by 2, right? This is what is meant by a rotation about the z-axis through an angle beta. So this is also a rotation operator. So every rotation operator, when we talk about single qubits, every unitary operator is describable by a rotation operator on the block sphere. So what we now have is a rotation on the block sphere. And if I precisely look at the picture here, if I start off as ket 0 and I switch on a magnetic field that points in z direction. So I start off with a quantum state, a spin which is aligned along the z-axis, and I switch on the magnetic field. So this is my time axis. And what I do is at time t equals 0, I switch on a magnetic field, some B. Corresponding to that B, there is going to be some frequency, omega. Okay? Now, when that B is switched on, a new Hamiltonian is switched on. A Hamiltonian becomes operative. That Hamiltonian is for time t equals 0 or above equals h bar omega over 2 sigma z. Now this Hamiltonian is switched on. This Hamiltonian is switched on. This quantum state will see the impact of a rotation operator. Will it evolve in time? In this case, it will not, because the magnetic field is pointing along the z direction and we are talking about rotations about the z-axis. So the field is already along the z-axis. So the field is not going to, the state is not going to evolve. This quantum state ket z is an eigenstate of this Hamiltonian. So if you look at this matrix here, sigma z, so H, so let me write down the matrix H when the field is pointing along the z direction. H bar omega over 2, the Pauli operator for sigma z is 1 here, 0, 0, minus 1. So what are the eigenstates for this matrix? So it has two eigenstates. One of them is 1, 0 and the other is 0, 1. So this is ket 0 and this is ket 1. So if your quantum state is this state or this state, and your field is also on the z-axis, no evolution will take place. Because the eigenstate is the quantum state is an eigenstate of the Hamiltonian. So this state remains conserved. And if the quantum state is an eigenstate of the Hamiltonian, the energy remains a constant of motion. That's called the Noether's theorem. If the quantum state does not change with time, it remains where it is, then it's an eigenstate of that Hamiltonian. However, if I put a magnetic field in another direction, suppose my magnetic field is now switched on at time t equals 0, but this field is now in a different direction, because magnetic field is a vector, right? You can point it in different, up, down, left, right, anywhere. You have a spin placed in it, and you have initialized your quantum state as ket 0. Now what you do is you apply a field B, which is say parallel to y. Let's keep it simple. Let parallel to x. So you put a magnetic field parallel to the x direction. The quantum state is ket 0. It's pointing in the z direction. So the spin is really aligned along the z direction. But now you apply a magnetic field along the x-axis. Now will the state evolve? Yes. Now it's going to evolve. And if you look at the Bloch sphere, you want to do a rotation about the x-axis. Because the Hamiltonian is now sigma proportional to sigma x. So this state will indeed evolve on the Bloch sphere. It's going to rotate on the Bloch sphere. And let's see how does it evolve. Quick question, is it getting clearer? And then I'll connect this with classical physics as well, with some electromagnetism. All of this is connected. In fact, as a spoiler, I would like to tell you that if you just have a single qubit, everything can be described by classical physics as well. Anyway, that's a spoiler, but never mind. Things get really interesting when you have 2 or more qubits. So now your Hamiltonian is, can you speak up the Hamiltonian? H bar omega over 2. Now this omega is proportional to the strength of the magnetic field. It's called the Larmor frequency. If you read basic physics books, that's what it's called. And now it's proportional to sigma x. So it's really H bar omega over 2. You want to write this in matrix form. This is what it is. And your initial quantum state is ket 0, which could be written as this thing in the Zeeman basis. Now your state after some time t greater than 0 is going to be e raised to power minus iota h bar omega over this h bar just goes away, omega t over 2 sigma x acting on ket 0. Yes?
So if I'm getting you correctly, you're saying that the flow of quantum information can be described classically?
Yes. For a single qubit. This quantum dynamics, this choreography of spins can be described classically as well. It's just magnets inside a magnetic field, nothing else. And I will ask you how to do that. Anyway, so if you look at this expression here, so we already have looked at a theorem. First of all, it's really immediately obvious that this is a rotation about the x-axis. Let me draw the block sphere first. I start off here. This is my x-axis. My magnetic field is pointing in this direction. I switched on at time t equals 0. And then this state starts to rotate about this axis. So when this starts to rotate, it goes here, right? It moves on this kind of great longitude kind of thing. This meridian. So how much does it rotate? How much? Omega by t. So omega is fixed because the magnetic field is fixed. It depends upon when are you measuring, when are you stopping your magnetic field, and what's your end point. So if I were to draw the magnetic field as a function of time, it starts off at some time t equals 0. Suppose it continues until time capital T and then switches off again. So depending upon how fast omega is, which means how big is the strength of the magnetic field, this state is going to revolve about the x-axis. So if the magnetic field is large, it will revolve faster because omega is fast, omega is high. If the magnetic field is short, it's going to rotate slower. And it depends upon what your end point is. It will end there. It's possible that it ends here. It's possible that it ends here. Anywhere, right? It can end anywhere. This angle will be omega capital T. Will it? So, because the square of sigma x is identity, and if I look at the theorem that I described, this is omega t over 2 ket 0 minus I sine omega t over 2 identity minus iota sine omega t over 2 sigma x, all of this acting on ket 0. Alright, so I've just expanded this thing. And if I want to look at what happens after time capital T, just replace this T with capital T. Now this is identity acting on ket 0. It will give me identity. Oh sorry, ket 0. So this, let's work this out. Cosine omega capital T over 2 ket 0 correct minus I sine omega t over 2. What happens when sigma x, the Pauli operator sigma x acts from 0? What result do you get? Ket 1. Because sigma x really is a NOT gate. If you work it out, it's a NOT gate. So this is ket 1. So if you map this on a block sphere, let's do a nice thing. If omega t is pi by 2, if your end time is such that this equals pi over 2 omega, what's going to happen? Omega t is pi over 2, this becomes 45 degrees. Pi over 4, 45 degrees. And this will become 45 degrees as well. So if you let omega t equals pi over 2, you're going to end up here. And this state is ket 0, 1 over under root 2 minus iota ket 1, right? This is what this state over here is. Alright. So, and if you stop here, you will end up somewhere here, you will get the corresponding state. If you keep on going, you just keep on moving on this big circle. After how long will you get back here? When omega t is it's 2 pi or pi? Okay, just hold on. When omega t is, so this is omega t is pi by 2, this is pi, this is 3 pi by 2, this is pi. So let's see what happens when omega t equals pi. When omega t equals pi, this becomes 2 pi, sorry. This becomes minus, because cosine of 2 pi over 2 is cosine pi, which is minus 1. Minus ket 0, minus iota, this becomes sine pi, which is 0, so I'm just left with this. So I end up with minus ket 0. But should I end up here? Because I get minus sign. So is this some new state? Or is it just equal to ket 0? It's just equal to ket 0 because this minus sign isn't mattering here. It's a global phase. Okay? So it doesn't matter. So if you do this amount of rotation, so how can you control the angle? There are two ways. Either you control how long this magnetic field is switched on, or you control the frequency, the strength of the magnetic field. And by the way, that's why it's called a spin half particle, because you have to do actually 2 rotations on the Bloch sphere to recover the original phase as well, in mathematical terms. So a spin 1 object is something that you rotate it once to get back to where you started off from. So that spin half particle, you have to rotate it twice. So it's a different kind of mathematical world. That's why it's called a spin half particle. So now we understand that with tuning the magnetic field, its strength and its direction, you can implement quantum gates. You can implement quantum dynamics. The state can evolve on the Bloch sphere in time. And you can do different kinds of, all quantum computing experiments work in this manner. So, probably you could give this as a homework problem. So here is my B Y, here is my BZ, here is my BY. So at time t equals 0, this is 0, I apply a field and I stop at some time capital T, T1. Then I turn on another field. From T1 to T2 it's operative. Then I turn on another field, starts at T2 and ends at T3. And these magnitudes can be different as well. So the omegas could be different. So in this regime, the omega, so let's suppose that the omega is proportional to the B. So in this regime, the omega is, let's call that constant of proportionality gamma. Some gamma. It also has a name called the gyromagnetic ratio, but it's called gamma. Gamma 1b here, and let's call this b1. So gamma 1b, gamma b1. Here it's gamma b2. Here omega 3 is gamma b3. And you can find out the Hamiltonians. Here the Hamiltonian is proportional to sigma y, here it is proportional to sigma z, here it is proportional to sigma y again. You can find out how that state works under these 3 regions. Starting off from some initial state, how does it evolve on the Bloch sphere? So you can do all kinds of gymnastics, do here, anywhere you like. You can do this dance of the quantum state on the Bloch sphere. How do you do a Hadamard gate? How do you do an operator of this kind, E minus I pi sigma x plus sigma z over under root 2? So if you were talking about spins inside a magnetic field, how will you implement the Hadamard gate? You would need to have a Hamiltonian that is proportional to sigma x plus sigma z, which means your magnetic field has to be tilted. So your magnetic field B has to be, so if I put a vector, some constant of proportionality gamma and then some other constant B, let's call it B, and x pointing in the x direction and pointing in the z direction at the same time, right? I would need a magnetic field of this kind. Sorry, this will be actually my this, yeah, and the Hamiltonian will be this gamma B sigma x over under root 2 plus sigma z over under root 2. So this is my vectorial magnetic field, and this is what the Hamiltonian it will create, which will evolve the magnetic field. Now I would like to end by a question. Why do I say that this can also be described classically? Yes. So what is the relevant equation here? So now I have a magnetic moment placed inside a magnetic field. What kind of equations do you need for that? What's the mechanics or the electromechanics for that? All of this can be done classically, by the way. When you place a magnetic moment inside a magnetic field, there is a torque acting on the magnetic moment, torque. And that torque equals the magnetic moment cross product with applied field. Here in this example, your magnetic moment was in the z direction, your magnetic field was in the z direction. So what's the cross product between mu and b? 0. So no torque acts, there is no spinning, no twisting on the Bloch sphere. There is no torque, there is no rotation. Quantum mechanically it also holds true, because now your state is an eigenstate of the Hamiltonian. So this quantum picture, this quantum language corresponds to the classical picture. In this example, here, this is the direction of a magnetic field. Your magnetic moment is pointing here. So what's the angle between these two classical vectors? 90 degrees. Mu cross B is now maximum. Mu B sine 90 is mu B is non-zero. So a torque acts. And what this torque does is, this is mu, this is B, it's going to rotate the magnetic moment. हाँ तो नहीं होगा ना, ये इधर नीचे जा रहा है. देखो, there are two kinds of torques. One is, so that becomes slightly complicated. There is a torque that causes relaxation and a torque that causes dynamics. So when the magnetic moment is finally aligned with the magnetic field, nothing else happens. But here, the torque is causing the magnetic moment to rotate about the axis. Right? So it keeps on rotating, because the torque is always operative. So this is our example of one physical system. Spin inside a magnetic field, and that spin inside a magnetic field is described in a quantum language. You can describe what the quantum states are. You can describe a Hamiltonian which corresponds to a magnetic field applied in a particular direction. And all two-level systems, all qubits can be described in this fashion. Even a photon's path can be described in this fashion. An NV center, the spin of an NV center, which is a vacancy in diamond, and one vacancy, you take out a diamond structure, you take out one carbon atom, you create a vacancy, you take out a neighboring carbon atom, you put a nitrogen there, it becomes an NV center. That's a very popular platform for quantum computing these days. The spin of a silicon atom is also another problem. All of this can be described in this picture. All of this is isomorphic to a spin-half system. That is why a qubit is called a fictitious spin-half. Everything can be described in this language here. Alright, so we start looking at quantum algorithms finally in the next lecture. Thank you.